So in this tutorial, which is basically part 2 of the previous, where we spoke about standard forms, here we'll be speaking about a new small concept called duality. We'll be covering some basic theory and look at a sample solved problem. Then you'll be able to solve a practice problem on your own. So first, when we speak of duality, we need to understand two major concepts. So one is the original problem that is given to us, which is also called the primal. It may be a maximization or a minimization problem depending on the question, and it will have m variables, and there will be a total of n constraints. Let's say some variables m and n. Then the derived form that we'll be getting is called the dual, and we will look at it shortly. We'll see the representation of the primal. So it's represented as a1 x1 plus a2 x2 plus so on till a and xn less than or equal to m1, b1 x1 b2 x2 so on. We have a set of some constraints. Let's say there are m constraints, and then we also have x1 x2 xn. So we can see that we have a total of n variables in each of those m constraints. So that means the problem is one of m variables and n constraints. The derived form that we get from the original, or that we need to get from the original, is also called the dual. And if the primal is a maximization problem, the dual is a minimization problem. If the primal is a minimization problem, the dual is a maximization problem. And if the primal had m variables and n constraints, our dual will be having n variables, and there were n constraints here. Here there are going to be m constraints. So if we took the primal as a matrix, we can see that the dual is a transpose of this matrix. So two things we need to keep in mind. First is the cost vector associated with the objective function of the of one, which we usually take as the original, the primal. It'll just be the right hand side vector in the other. So what in the other set of constraints. So what we mean here is we have our objective function, right? Z is equal to max a1 of a1 x1 a2 x2 so on till a and xn. So these coefficients a1 a2 so on till an is going to appear on the right hand side of the constraints of the other. So if a1 till an are the coefficients of the objective in the primal, they're going to appear on the right hand side of the constraints in the dual. The second thing to keep in mind is that the constraint coefficient matrix associated with one problem is simply the transpose of the constraint coefficient matrix of associated with the other. So one, how we can visualize this, I already told you one problem, let's say the original has m variables and n constraints, then that is going to get transposed into n variables and m constraints. If we visualize this as a matrix, we have the coefficients of the constraints a1 a2 so on till an, b1 b2 so on till bn. We can write these coefficients as one matrix, constraint coefficient matrix of the primal. So if we take the constraint matrix associated with the dual, it is going to be the transpose, as in the rows and columns of this matrix are going to be switched to the columns and rows of the other. So the matrix, the transpose is going to look like a set of constraints ending with b1 a1 or b2 a2 and finally bn and an. So this is nothing but a simple representation. We'll be able to understand these things better when we take a sample problem and solve it simultaneously side by side. So we'll try and write the problem down and solve it just adjacent to it to get a clearer understanding. So the problem we take, let's take a minimization problem. Z is equal to 5x1 plus 8x2 plus 4x3, and we have some constraints 2x1 plus 3x2 minus x3 greater than or equal to 10 so on, and the greater than or equal to constraints. All our constraints have the greater than or equal to sign except one, the one that we are writing right now, which has a less than or equal, which means we should convert it by multiplying by -1 because we want all of them to be uniform and have the same sign. Now let's write the objective of our dual. Max z star is 10y1 plus 5y2 minus 7y3 plus 9y4 plus 6y5. How are we getting this? This is basically the right hand side of the constraints of the primal. So we are taking a new variable y, y1, y2 and using these coefficients to write the objective of the dual. This is a standard procedure we need to follow. Our first constraint is 2y1 plus y2 minus 2y3 plus 3y4 plus y5 less than or equal to 5. How are we getting this? These are the coefficients of the variable x1: 2, 1, 2, 3, and 1. 5 we are getting from the x1's coefficient in the objective function. Minimize it. Next constraint is 3y1 plus y2 minus 5y3 minus y4 plus 5y5 less than or equal to 8. So you can guess now, these will be nothing but the coefficients of x2: 3, 1, 5, minus 1, and 5. We write it with the y variables y1 till y5, and we are getting 8 from the objective function of the primal again. Then our last constraint, minus y1 plus 3y2 plus 2y3 plus 3y4 less than or equal to 4. And are obviously a greater than or equal to constraint y1 till y5 greater than or equal to 0. This once again, as you must know by now, we are writing coefficients of x3. So we can see that we had 5 constraints here, we have only 3 constraints here. Objective function has 3 variables, but here we have 5 variables. This is what we meant when we said this is a transpose of that. I hope this concept is clear now. Thank you for watching.